In a set of n elements, determine the minimum value needs n-1 comparison are indeed necessary? Why? So let's consider a very specific example. Let's consider an array A with 5 elements. Let's say A is equals 3, 1, 4, 1, 5, and then we start with the first element and consider it as our minimum. So initially minimum is equals 3, and then we compare the next element A of 2, which is 1, with our minimum, but 1 is less than 3, so we update minimum, now it's become 1, and then we compare the next element A of 3, which is 4, with our minimum, which is 4 is bigger than 1, so there's no update needed, and then we compare the next element A of 4, which is 1, with our minimum, which is 1 equal to 1, so no update needed because they are equal, right? And then we compare our next element A of 5, which is 5, with our minimum, which is 5 is greater than 1, so there's no update needed. After 4 comparisons, since we have 5 elements, the minimum value determined is 1, so every new element after the first one was compared to the current minimum, and if there's a smaller one was found, then the minimum was updated. So this approach guarantees us to finding the minimum with n-1 comparison, because each element except the first one needs to be compared to establish if it is smaller than the current known minimum, right? So each comparison either maintains or updates the minimum, which will lead to a linear number of comparison, which is related to the numbers of elements. Let's talk about the fundamental principle in computational theory, which is related to determining the minimum or maximum in a list of elements, which rely on comparison-based methods. Let's try to explain by using the tournament analogy to illustrate the lower bound of n-1 comparison, which is needed to determine the minimum in an array. So we can imagine how to organizing a tournament where each element of the array is competes against another element in this comparison, right? And then the winner is the smaller elements, or larger if we try to find the maximum value, right? So this winner will keep move on to compete in the next round. Let's consider we have an array of elements A, which is 6, 2, 9, 4, 3, and 8, with n is equal 6. So we are assuming they are pairwise matchups. The first round of the comparison is 6 versus 2, the winner is 2, and 9 versus 4, the winner is 4, and 3 versus 8, the winner is 3. So the total comparison in this round is 3. And in the second round of the comparison, 2 versus 4, the winner is 2. And 3 has only 1 less element, right? So 3 automatically proceeds to the next round or completes if it is an odd number of winners present, right? And then it is have total comparison in this round is 1, and the final round of the comparison is 2 versus 3. The winner is 2, so the total comparison in this round is also only 1. So the total comparison we made is 3 comparison in the first round plus 1 comparison in the second round and 1 comparison in the final round, which is equal to total 5 comparisons. So the key point is every element except 1 loses once. In this array of 6 elements, every element except the winner, which is the minimum element in our example, has lost at least once, which is inherently implies that at least 1 comparison per losing element, which amounting to n-1 comparisons. So optimality, the minimum number of the comparisons we require to determine the minimum or maximum elements in such a scenario is proven by a fact that each element needs at least 1 decision to be either eliminated or declared as a winner, except the last remaining element. Thus, any algorithm that tries to find the minimum or max by direct comparison and updates, like the minimum algorithm we showed earlier, is optimal because it performs exactly n-1 comparisons. So this analysis underscores why the minimum max algorithm is optimal in terms of comparison count, as it adheres to the theoretical lower bounds for the problem type.